Hi. In this third video in the series, I'd like to demonstrate how one can generate model from circuits using MODELFIT. The example I'm going to use is again the continuous time linear equalizer, which has a topology of a differential amplifier with capacitive degeneration. Generating models using MODELFIT is somewhat different from using MODELZen. In case of using MODELZen, it did not require any information from the designer. It was a push-button flow. But with MODELFIT, it can generate better models in terms of speed and accuracy by leveraging the expertise of the designer himself or herself. For instance, one can decide to model this CTL circuit as a linear filter with some DC nonlinearity included. That intent can be expressed in a template model, which describes the CTL model as a combination between a piecewise linear function and a linear filter. So this piecewise linear function models the DC nonlinearity part, while this filter primitive models the AC linear system part. These add blocks before and after these two primitives performs a conversion between the signals and the common mode and the differential mode, and vice versa. Generating model using MODELFIT generally involved writing a Python script using the MODELFIT library. In this demo, we have written a script named fit_ctl.py, which is Python library which performs a spice simulation at first using the hspice function provided in the XMODEL library, and reads in DC simulation results contained in the .sw0 file, extracts the DC transfer characteristic between input and output, and fit that result into a piecewise linear function using a MODELFIT function. As a second step, it reads in the AC simulation results contained in the .ac0 file, reads in the AC transfer function between input and output, and this time fit that into a filter primitive using the same MODELFIT function. And the final step is to generate model by populating numbers in the template. Let's see how it runs. When you execute this Python script that I just explained, it will first run the hspice simulation and fit the DC simulation results into a piecewise linear function. In the next step, it will fit the AC simulation results into a filter primitive. And finally, it will generate the model. The resulting model has the same structure as the template as I explained, but it contains these numbers populated by the script. It contains information regarding the DC transfer function as well as the location of the poles and zeros. Now, we'd like to see how well this model works in simulation. To do that, I'm going to run this transceiver simulation again, one with the spice netlist using COSIM, and the other with the model that I just generated using MODELFIT. The test bench that I created for doing that is called tb_func. I'm going to run it. Now it is running a VCS simulation along with the XA co-simulation feature, and it will soon be done. It's done. Let's see the waveform results. Open the X-Wave and plot the waveform using spice netlist, and plot the waveform using the model we just generated using MODELFIT. As you see, the two waveforms agree very well. And if I toggle the events on the waveform, the X model generates far fewer events than spice, indicating a faster simulation speed. In fact, this number of points on the green one, which is the XMODEL simulation, is fewer than the one you've seen with Model Zen because the model we generated using MODELFIT is much simpler. This is in general true. The model you created using the design expertise is more effective in terms of speed and accuracy. However, the burden is that it requires input from the user. Hope this gives you an idea on how you can easily create model from circuit either using MODELFIT and Model Zen. We at Scientific Analog are working hard to make this interface easier and simpler. So please stay tuned. Thank you.